All right, we're working on Unit 1, Atomic Structure and Properties. We're looking at moles and molar mass. Our learning objective is to be able to calculate the quantities of a substance or the number of particles using dimensional analysis and the mole concept. Our second essential knowledge is that Avogadro's number provides the connection between the number of moles in a pure sample of a substance and the number of particles of that substance. So this idea of a mole was created because atoms are so small that we can't count them by looking at a sample. So we had to find a way of relating the number of atoms to how much they weighed or their mass. To do this, a set point had to be determined. And the mole was defined as the number of atoms in exactly 12 grams of carbon-12. So 1 mole was found to be 6.02 times 10 to the 23rd atoms of carbon-12. By setting the definition to an exact isotope of carbon, an exact atom, and an exact mass, we can relate this to any other element or atom. And we now call this number Avogadro's number. So Avogadro's number is the 6.02 times 10 to the 23rd particles, and that's equal to 1 mole. And this is a huge number because particles are so small. And when I say particles, we're talking about things like atoms or molecules, ions, formula units. We can't see these individually, so we're going to have to mass them out instead. Now, using Avogadro's number, I'm able to keep track of the number of particles going into a reaction and coming out of a reaction. It lets me plan my chemistry and make sure I'm not breaking any laws of conservation of mass. It's the number that allows the bookkeeping in chemistry. So let's look at an example. A sample of carbon in a glass vial was known to have 3 moles of atoms. How many carbon atoms are in the sample? First thing we're going to do is annotate that problem. So we're going to underline 3 moles. We're going to put boxes around substances, carbon and carbon, and we're going to circle my question. How many carbon atoms is what I want to know? So my plan is to go from moles to atoms. And to do that, I'm going to need Avogadro's number. The key between moles and atoms is Avogadro's number, 6.02 times 10 to the 23rd particles per mole. Now, this is just simple dimensional analysis. I don't need to go to the periodic table. The carbon is extra right now. I know I have 3 moles of carbon, and there are 6.02 times 10 to the 23rd atoms of carbon in 1 mole of carbon. Again, dimensional analysis, we're lining up our units. Moles of carbon are going to be canceled out by the moles of carbon on the bottom, leaving me with the atoms of carbon on top. And I'm just going to plug this into the calculator. 3 times 6 is about 18, so we're going to get 1.8 times 10 to the 24 atoms of carbon. That's simple. Let's look at another example. If a sample of silicon contained 2.53 times 10 to the 24 atoms of silicon, how many moles of silicon would that be? So this one's the same idea, but in reverse. I'm going from atoms of silicon to moles of silicon. So my plan is to convert from atoms to moles. To do that, I'm still going to need Avogadro's number, and that's 6.02 times 10 to the 23rd particles per mole. And I'm going to set up my dimensional analysis. Again, 2.53 times 10 to the 24 atoms of silicon is what I'm starting with. I know that 1 mole of silicon is equal to 6.02 times 10 to the 23rd atoms of silicon. Notice my unit on top, my unit on bottom. And I'm going to plug it into the calculator and I'll get 4.2 moles of silicon. So Avogadro's number allows me to keep track of the number of atoms so long as I know the moles, or if I know the number of atoms, to get to the number of moles.